Okay, so welcome everyone. This is Foundational Science, setting the stage for success. Focus on grades 6 through 8. If that is not your main grade band, I'm going to be doing a 3-5 version of this presentation right after this, and then a K2 version at 140. Something, the last session, session 5. So yeah, in this session, we're really going to focus on some of the non-content based science stuff that you can be doing, that you can do in your classrooms, or that you already are doing in your classrooms and might just not even be realizing it. We're going to hopefully make this a productive session where we're going to have a few 10 to 15 minute blocks of kind of collaborative work time on some Jamboards, because really I want everyone to just be able to walk away with some new resources. It's really going to be a collaborative session. So let's get going. So my name is Cassandra Armstrong. I am like all the other presenters here today. I am a curriculum writer and professional development specialist at IMSA. My personal focus is on K12 STEAM teaching and learning. That is what my kind of passion is. I was a high school science teacher for almost 10 years, a little bit in Michigan, sometimes, or for the most part in the city of Chicago. I taught biology, chemistry, physics, environmental science. Really, if it was able to be taught at the high school level, I taught it. And since coming to IMSA, oh dear, sorry, there we go. All my notifications are stacking. There we go. So since coming to IMSA, I've really focused. I started out working on this kind of 3-5 grade band, then worked on a preschool STEAM curriculum, and now kind of getting back into some of the middle school and high school stuff. So really just my personal passion and focus is on good science learning overall for students. Come on, there we go. So we have a few objectives for this session. Like I said, we're going to look at the 3 dimensions of science as they apply to 3-dimensional learning. This is from the Next Gen Science Standards, and we'll talk a little bit more about that in a bit. You're probably familiar with them. If not, we'll do a really quick overview. But like I said, we're going to focus on not so much the DCIs, which are the content-based dimension of the NGSSs, but we're going to take a deeper look at the science and engineering practices and the cross-cutting concepts. And then we're going to look at the progression of skills as they build from 6th to 8th grade. So specifically in that middle school, those middle school years, what is the kind of targets? What should students be doing in terms of the SEPs and the CCCs in the middle school years? And then we're going to just look at ways, like I said, collaboratively together to provide learners with opportunities to build a strong science foundation. So what are you doing? What could you be doing? How could you tweak things that you're already doing and make that with a little tweak could make a big impact? So those are some of the things that we're going to focus on for this session. Our main resources for this session, the first one is a framework for K12 science education. I use this book, I'm not going to say daily, but pretty much daily. It's amazing. You can buy it for, I think it's usually like $35-40. If you're a digital person, you can download the PDF for free. If you want to, print it out and put it in a binder for yourself, or obviously just view it on your computer. But there's so much in this book. All of the kind of targets that we're going to talk about and focus on today are from this book. So I just want to make sure that I give credit where credit is due. This was kind of like the book that the Next Gens were we're based off of. And so then we have our next generation science standards, which are, is kind of our secondary resource for this presentation. We're going to, again, look at the SEPs and the CCCs, and then really focus on a couple of the actual standards at the middle school level. So this is, again, a quote right from this book. And it's kind of the why and the because. Why did the next gens even get made? Why did we need science education reform in the United States? All of these things. So we have this quote, and I'm just going to read it. The overarching goal of our framework for K12 science education is to ensure that by the end of 12th grade, all students have some appreciation of the beauty and wonder of science, possess sufficient knowledge of science and engineering to engage in public discussions on related issues, are careful consumers of scientific and technological information related to their everyday lives, are able to continue to learn about science outside school, and have the skills to enter careers of their choice, including but not limited to careers in STEM. So really, it's like, why do we teach science in schools? Why is it important? And it's kind of interesting as an educator to take a step back and consider that, because why do we teach science? If I think back to some of the biggest, projects or most memorable activities that I did in science in high school, it was things like building a cell model, which, yes, I'm a science teacher, but I can say outside of my science teaching education, I've never needed to use a model of a cell, right? Like in my everyday life. Or like, I'm not going to say I don't use stoichiometry, because I actually kind of do. I really enjoy cooking, and I can make that relationship work. But, there are just so many things out there. Building the marble roller coaster in physics. Like, it's a really cool project. I remember it. I loved it. But I don't really remember why I did it, other than it was a fun, science project. So like, why this is the purpose of science. And science education. We want students to appreciate science, because science, it says the beauty and wonder of science, because science is beautiful. Anyone who loves looking at a sunset or a sunrise or anything like that, I mean, science is beautiful. I think we have the next couple points. We've really noticed, not to get political by any means, but over the past couple of years with the COVID-19 pandemic, possess sufficient knowledge of science and engineering to engage in public discussions. I think anyone who has watched the news or has a social media account where they have seen other discussions taking place, I think we can kind of all agree that a lot of people don't possess sufficient knowledge of science to be engaging in the types of discussions that they are. Are careful consumers of science and technological information related to their lives. Again, reading an article that someone found on Facebook and believing it to be true, that's not being a careful consumer of scientific information, because that we don't know where that source is. We didn't do the research. So these are the kinds of things that, we want to keep in the back of our mind of, we don't, our students might not necessarily need to know the purpose of a ribosome or the mitochondria in their everyday lives, but these are the big overarching goals that, as scientists, these are some of the skills that they should have. And when they leave school to go to college or career or trade or whatever, they should, have a good working knowledge of this type of information. And then, so our next thing is these guiding principles. So that's kind of our end goal. How do we start? How do we get there? How do we know that, these three dimensions work? Well, children are born investigators. I have a 2.5-year-old and I have a 5-month-old, and I have, you know, before I had kids, I read this and I'm like, yeah, kids are curious. They always ask why. No, like watching my kids just look at something and study it. Like my 5-month-old, you know, just the simplest thing. She looks and you can tell her little brain is just like, how does that work? Like, why, what is this new thing that I'm looking at? My son is already a tinkerer. He loves, you know, just playing with things and trying to figure out how they work. It is a natural instinct. And this is an instinct that we need to, as students go through school, we need to really push for this their born investigative instinct to really thrive, because I'm sure this is the middle school session. I'm sure middle schoolers are reaching the peak of their anti-investigation, right? They're way more worried about being right versus wrong, not wanting to make a mistake, things like that. So again, this is something that we can work at starting at, you know, preschool, kindergarten, as parents at home. We really need to get rid of the stigma of being right versus wrong, because scientists are wrong all the time. Like the majority of the time, scientists are wrong. So we really just need to get away from this idea that being wrong is bad, so that students aren't afraid to be wrong, so that they aren't afraid to, you know, take chances and do these investigations. The next guiding principle is to focus on core ideas and practices. So this is our content. So yes, designing experiments is amazing, collecting data, doing data analysis on tables and graphs. And those are all incredibly important skills that we're going to focus on today. But this is still science, and there are core ideas in science that, you know, there's a reason we study the cell, right? It might not necessarily be to remember that there's a ribosome and a mitochondria and a nucleus and all of that, but the fact that these organelles are all part of a system, and that system works to build the basic unit of life. And, you know, so really just the fact that there is a reason that we learn these things, and that there is science behind it. So this presentation is not to say that the content is not important, but we're just going to focus on how we can enhance some of those other things. The next thing is to understand that understanding develops over time. So again, these guiding principles are from this book. And some of what we're going to look at today really focuses on this understanding develops over time. So all the three dimensions, the disciplinary core ideas, the science and engineering practices, and the cross-cutting concepts, they all build on each other. So there are 7 cross-cutting concepts. The first one is patterns. And so like what we're going to look at today is what is expected for students in middle school to understand about patterns. And in the handouts on the Google slide, when you click, you know, download materials or materials download here or something like that, you'll be taken to Digital Commons. And for this presentation, there's the PDF of the presentation, but there's 7 other documents, and I'll explain those in a little bit. But the documents all have the K2, 3, 5, 6, 8, and 9, 12 expectations for each SEP, CCC, and DCI. So while we're focusing on the middle school ones, if you want to know, well, my students aren't going to be able, you know, by the end of 8th grade, they're not even, you know, at the 3, 5 or the K2. So you will still have that information. Like what should this be building upon? If we need to go back and review some of the skills from the 3, 5 band or something like that. So the main idea that this understanding develops over time is that, yeah, learning something new in middle school or high school is obviously going to happen, but it's going to be based on a skill or content, you know, nugget that they have that the students have at least heard or practiced at some point previous in their school career. Hopefully, you know, that's kind of the goal, is that what starts in K2 builds upon in 3.5, then builds in 6.8, then builds in 9.12. The next bullet is that science and engineering require both knowledge and practice, kind of like what I was saying before. You know, if I think back to middle school, elementary school science, it was a lot of worksheets, a lot of vocabulary, a lot of fill in the blanks, you know, doing math type problems based in science and things like that. Those are, you know, those are important things. When I was doing my student teaching, my mentor teacher told me that I was in a high school biology classroom, and she told me that she had read a study that equated a high school biology class to be similar to a first year language class, because there is so much new robust vocabulary that students need to learn on top of understanding how that vocabulary all works together. So it's not just the content, it's not just the practice, it's really making sure these three dimensions meld together so that students understand what they're doing, but why. We also want to connect to students' interests and experiences. This is why the NGSSs, it's not just a list of lessons. Like, it's not a textbook with, okay, you're going to do this lab and then this lesson and then this activity, etc. It gives teachers the freedom to explore these ideas in a way that will relate to their students, because you are the teacher, you know your students best. And also, I always, you know, say that, you know, that's something that's commonly said, right? You're the teacher, you're in your classroom, you know your students, but you also know yourself. And this is something that I've been discovering in the past couple of years as I've worked with a lot of teachers, is something that works for me might not work for you, because teaching is so personal. Right? You know, it truly is a part of your personality and who you are as a person. So if something fits my personality and doesn't fit yours, that's okay. So just knowing that we might then run our classrooms a little differently. So we can use that to connect to students' interests and experiences, and also your own. You can, you know, the same concepts can be studied many ways. And then the last guiding principle is promoting equity. So we want all students to be able to learn this material, the content, the practices, the concepts. We want all students to be able to learn that, knowing that not all students will have access to microscopes or, you know, fancy lab equipment and things like that. So the standards were written in a way that does not require any of that. There are ways to explore these ideas with basic classroom materials. Now it might not be as easy, or, you know, things like that, but there is, to be equitable, we need to make sure that we're not setting expectations for schools that cannot meet those expectations. So, it was kind of a lot to go through. Again, I've mentioned the three dimensions are the disciplinary core ideas, which is our content, our science and engineering practices, which is kind of like our what scientists and engineers do, kind of like your old school version of like the scientific method. And then your cross-cutting concepts are themes that we see across all sciences and a lot of times other contents as well. So we have 8 science and engineering practices. Like I said, this is kind of like your classic scientific method, but better. Scientists ask questions, engineers define problems. We develop and use models to represent things that are too big or too small for us to see in the natural world. We plan and carry out investigations, analyze and interpret data. We use mathematics. My math my math teachers don't like it when I say this, but I always told my science students that the only reason that we use math is to understand science, right? Math makes science make sense. We construct explanations and design solutions, meaning using evidence to argue. And we then communicate that information. So these are the things that real scientists and engineers do on a daily basis. Our disciplinary core ideas, we have our three main physical sciences, life sciences, earth and space sciences, and then there's another category for engineering and technology. And then lastly, our cross-cutting concepts. These are our themes: patterns, cause and effect, scale, proportion, quantity, systems and system models, energy and matter, structure and function, stability and change. These are things that you will find in the life sciences, in the physical sciences, in the earth and space sciences, in engineering, and outside. You'll find these things in mathematics, you'll find them in literacy, you'll find them in history. So all of that being said, let's go and take a look at our first activity. So the first activity is we're going to look a little deeper at the science and engineering practices. So this is a Jamboard. Let me click into my Jamboard. And I believe you should all be able to see that. So I'm going to, in the chat, send the link for everyone to join. And what I want to do, I will reshare my screen back to the instruction page as people come into the Jamboard. And what I want us to do is just have this be a really collaborative session where we can just examine what we're already doing and any ideas you have, any resources. So as you read through the Jamboard, there's 8 different slides you can click through at the top. There's one slide for each of the SEPs. And then there is a kind of definition, like in middle school, for asking questions and defining problems. We want our students to be able to, that should say progresses, not processes, progresses to specifying relationships between variables and clarifying arguments and models. So that's kind of our overarching goal for asking questions and defining problems in middle school. And then there are all of these bullets that are kind of like, here's some examples of what a student might be able to do. And this is by the end of 8th grade. So for each slide, you do not have, you know, there's 4 options for sticky notes and there's 8 different slides. You do not have to do whatever 4 times 8, 32 different sticky notes, just whatever sticks out at you. If you really focus on, you know, using mathematics or whatever, one of the other SEPs, then focus on, go to that slide and start there. But what I want you to do is, if you do something in your classroom that, like an activity, a lab, a concept, where you are like, oh, my students do this in that activity, I'm already doing this, jot it down on a green sticky note and put it on the page. If you see something that is like, oh, well, I know that patterns is a cross-cutting concept, this would tie in really well with patterns, put that on a blue sticky note. If you see something about engaging in argument from evidence and you use news ELA articles in your science classroom and think that might be useful to others, stick it on a pink sticky note and say, you know, here's a great virtual resource for that ties in well with this one. And then if there's one that just doesn't make sense to you, write any questions, concerns, comments on an orange sticky note. So I will leave this up here. Go ahead and start stickying. Let's go for about 10 minutes, 5 to 10 minutes. We'll see. I don't want to cut anyone off. And I'm going to add some of my own on there as well. I want to make sure you guys can still see the instructions though. Okay, I think that's good. And feel free to chat or shout out if you have any questions about the Jamboard. The sticky note button is on the side if you've never used a Jamboard before. Okay, so it's been almost 10 minutes. So let's go ahead. I know this isn't a ton of time, but like I said, I'll leave this open for a little bit for the day. And then I'll turn, if you want to go back and add stuff, and then I'll turn it into a view only. So there's a few things for asking questions and defining problems. On the first slide, there's a making soda stoichiometry lab, and I added that one. It might be a little advanced for middle school, but it's something that I had done in my chemistry class where students had to kind of develop, it fits in a few of these because it was kind of a whole scientific process, but it started with, you know, how can we take juice and turn it into soda? So, you know, well, it needs to be fizzy. How can we make things fizzy? And it's this whole kind of work through that follows that process. Let's see, developing and using models. So someone said toothpick bridge project. Yeah, that's a perfect example of a model. Bridges are huge. If we think of like the Golden Gate Bridge, we can't build a model bridge that is at, you know, at size, because that would be crazy. And so using a toothpick bridge is a perfect example of developing and using a model. I love it. Planning and carrying out investigations, bottle biomes with different water supplies. Perfect. Yeah, so, and that again relates to a bunch because I'm sure there's like a guiding question there and things like that. Does anyone want to, if anyone wants to speak out, feel free to, about the toothpick bridges or the bottle biomes. Okay, nothing.
Those projects were for my middle school kids.
Okay.
With the biome project, we researched local soil samples and local water sources to see what we thought might be the best options.
Okay.
And then we planted hyssop seeds in there to see which ones would make the best, produce the best plants. So we had like pond water, we had creek water, and lake water. So
yeah, that's awesome. That sounds like a perfect investigation. And like you said, it, you know, it hits a lot of these bullets where it's hitting using multiple variables, and to figure out which is the best, they'll have to use the evidence from their, you know, which plants grew best in which environments and things like that. So yeah, it's perfect.
And then the toothpick, we also did the toothpick bridge project. And we relate that to the animal crossings for our ecology unit and which ones would be best.
Yes, the book, the Animal Crossings book, is that what you're talking about?
Well, we go through and we use the videos from like Utah and stuff where they have, so they can see different examples and things like that.
Yeah, I love that because we actually in the preschool unit there's like a little kids book that I think it's called Animal Crossings, but it's a great engineering design kind of experiment activity. I love that. Perfect. Thank you. Yeah, so there's some other things using mathematics. I again, I've been out of a school for a few years since coming to IMSA, and IMSA is residential. So we're not in the classroom as much there. So I don't know what the current kind of rules on cell phones in the classroom are. But cell phones can be really great digital tools. So some of these, the first one says using digital tools to analyze large data sets, calculators, things like that. But our cell phones have so many great technological tools these days that I know that a lot of classrooms are starting to embrace the cell phones versus banning them. And obviously it depends on your classroom, your school rules and things like that. But yeah, cell phones can be a great tool. There's a few here. Love Rube Goldberg. I saw a TikTok and someone had made a Rube Goldberg with, what are they called? Like xylophone tile things. And the ball, as it went through the Rube Goldberg, hit all the tiles to play a song. There's like an Indiana Jones one and Up from the movie Up. It was adorable. So I love that. Shark Tank. And that's a great, a Shark Tank type thing is a great way to do some integrative stuff with like entrepreneurship, creating a business. There's a lot of amazing things to do there. An egg helmet design challenge. Yeah. Classic. It's, if it ain't broke, don't fix it. It's perfect. Yeah. So I'm going to go ahead and move on, but these are here. And I'll keep it open in case anyone wants to, thinks of something or wants to contribute further or wants to go back and look. So, okay, we did our debrief. So like I said, some on the Digital Commons page, and I actually looked, I'm not sure if you guys can see my screen. For some reason, this session they're not loading the attachments, but the other sessions, the 3.5 and K2 have the same downloadable attachments. I'm not sure why they're just not showing up there, but these are included in the downloadables for this session. And what we just had listed was what you just saw on the Jamboard was the science and engineering grades 6 through 8 and all the bullets there. But I know a lot of people are interested in knowing, what kind of skills students should be coming to them with. So some of those 3.5 or K2, or if you have students that are advanced and you're trying to prep them, for high school sooner, maybe looking ahead. So these downloadable progression guides have everything. And again, it is all from the framework for K12 science education. These are just kind of a prettier, more usable version. So we're going to now do the same activity, but with the cross-cutting concepts. So let me share that again in the chat. And so this time, just a little difference if in the stickies. The green sticky note is going to be for science ideas. So like the first one is patterns. What are some cool, middle school science activities that you do that might focus on or have students think about patterns? Blue might be a non-science idea. So like the Shark Tank thing, yes, that's science, engineering, design, but that's also something that is easily integrated or can be done in other courses. And that's kind of to get you thinking about who you could reach out to at your school to do a collaborative project with. Pink is still resources or useful links, and then orange would be any questions, comments, concerns. So I will leave that up there. And there are 7 of the cross-cutting concepts. Again, so it's just like before. Oh, request access. Let's see. Oh, goodness gracious. I thought I went through and did all this yesterday. Okay, I just changed it. It should be good now. Sorry about that. Okay, yeah, I see people popping in. Excellent. So again, I'll go on mute and just take a few minutes. Again, I wish, in hours, it's hard to fit so much into an hour, but I'll go on mute for 5 to 7 minutes so we can work collaboratively on this Jamboard for a few. Okay, so we have 5 minutes left, so we'll go ahead and kind of wrap up on this one. Instead of going through each one, is there, I'll do one that I like because it can be used at any grade level, and I put it on stability and change on number 7. And it's the human stimulus response. So this is something that you could explore anywhere from kindergarten to 12th grade. Something as simple as what happens when our bodies get too warm. They sweat. We shiver when we're cold. It's all about these feedback systems with homeostasis that our bodies have. Does anyone else have one that they want to share before we wrap up? Oh, thermal energy popcorn lab, love it. Yes, the interaction between Earth systems. Sorry, I'm going backwards now. That's huge, and a great way to even kind of go into like the energy cycles. On the next one, digestive system, excellent. Yeah, making models is so fun. Scaled diagrams of the solar system. Yeah, with patterns there, I mean, we could go on about patterns for days. Looking at patterns and relationships in data is I think probably one of the most important middle school science tasks. So yeah, perfect. So similar to the other one, I'll leave it open for a little bit and then I'll change it to view only in case you want to go back and take a look. So really quickly to wrap up, just an example, middle school performance expectation. So that's kind of what the standards are called all together. So here's a middle school life science one. It says develop a model to describe the cycling of matter and flow of energy among living and non-living parts of an ecosystem. So looking at this matter and energy cycle through an ecosystem. So if you go on the NGSS website, it's nextgenscience.org. The performance expectations are set up like this. And then if you mouse over them, it kind of tells you what you're focusing on. So here's the same standard, but now we've separated it. So the science and engineering practice that we're focusing on is developing models, develop a model to describe. The cross-cutting concept, the theme that we're focusing on is the cycling of matter and flow of energy. And then the disciplinary core idea, the main content that we're focusing on is living and non-living parts of an ecosystem. And so when you go to the website, it will look like this. And where you mouse over each part, it connects and then shows how this is really truly becomes a 3-dimensional kind of goal where we're learning the science content, the science skills of using models, and then those themes that we see across all sciences. Yeah. So the very last thing, how do we, kind of get these going in our classrooms and try to focus? You let your students play, give them an idea and give them a class period to try to develop questions and strategies and design experiments on their own. Give them tools. If you don't have tools, use, we do what we call like dollar store science a lot of times. You can get, knockoffs for scientific tools, or use cell phones, or, something other than a pen and paper. Give them some sort of technology to allow them to study these things. And then it's okay to make mistakes. Take the pressure off. Get out of this right versus wrong environment, and let students know that it's okay to make mistakes, and persevere through those types of hardships in the classroom. So I just want to say thank you guys for listening to me for the past hour. Hopefully the Jamboards were a little kind of fun break from the listening. When you go back to the main page, there's 2 surveys, the IMSA survey, which is kind of like my personal evaluation, and then the ISB evaluation, which is what you fill out to get your CPDU credit. And then there's the materials download. That's the QR for the materials download. Like I said, this session, for some reason, it wasn't popping up. I'll check in on that. But if you go to my other sessions, it's the same materials. So once again, thank you so much. I'll stay on for just a minute if you have any questions or anything, but it was, thank you for attending, and it was nice to talk with you all.